Okay, I'm going to go back and hit examples, or example 2, and then we'll do example 3 in this video. Do these in green. Okay, and actually I'm going to do part B of example 2 first. So here we're using more of the second fundamental theorem as opposed to the first, or the accumulation functions. We are looking for values of a function when we are only given the graph of its derivative or its rate of change, okay? So we have the graph of f prime. We also do know that f of 0 equals -3, so we have a point on the original function at 0, -3. It's a point on f. And then we also know that we can use the second part of the fundamental theorem, and actually in this rearranged order, we can use that, or we can use the order it's originally written in, to we have a starting value 0, -3, and then we can use f prime as an accumulation function, or we can write an accumulation function there to find a new value. So again, it's kind of like we have a starting value and we have a rate function, and we can accumulate that to figure out the ending value. So again, I'm going to do part B first, and I'm going to go ahead and use this form, this AP's favorite formula rearrangement of the second part of the fundamental theorem. So f of 3, the after amount, is equal to the initial amount f of 0, okay, which I know f of 0, plus the accumulation from 0 to 3 of f prime of x dx. Okay, plugging values in, f of 0, so this is equal to -3, plus, and now I need the accumulation from 0 to 3 of f prime. Well, we know that that definite integral from 0 to 3 gives us a net area, so area above minus area below, and I'm looking on the interval from 0 to 3. And we're going to do this geometrically. So I have this triangle here that has an area of 2, and then this triangle here that has an area of 1/2. However, my integral finds net area, so it's 2 minus 1/2, okay, which is a total, so -3.5 plus 2 is -1.5. So total of -3/2. Okay, for the second one, I'm going to do this one, since -4 is to the left of 0, I'm going to do this one with the fundamental theorem written in this order right here. Okay, the original order there. So I'm going to write the integral from -4 to 0, because order does matter, and I need to go from left to right. So -4 to 0 of f prime of x dx is equal to f of, and again, order matters, I need to do the right value, so f of 0 minus f of -4. Okay, and I'm going to switch colors here for the graph. So the integral from -4 to 0 of f prime of x dx is going to be represented by the area that is under this semicircle on the interval from -4 to 0. So I'm going to think of this as a rectangle that's a 2 by 4, so that has an area of 8, minus the semicircle, which would be, let's see, half of 4 pi, so minus 2 pi. Okay, so this shaded purple region outside the semicircle has an area of 8 minus 2 pi. Okay, so 8 minus 2 pi equals f of 0, we are given as -3, minus f of -4, the thing we're trying to find. Okay, so adding f of -4 to both sides and subtracting this whole thing, we get f of -4 equals -3 minus 8 is -11, minus -2 pi, so plus 2 pi, or you could write that 2 pi minus 11. Okay, all right, and then lastly for this video, we're going to do example 3, and we'll save rate in and out problems for later. Okay, so we're looking again at a graph of f prime. It is given, it's actually not labeled over here, but it says in the words that this is the graph of f prime, the derivative of f. So I'm going to label this f prime. It's 4 line segments, 1, 2, 3, 4, and 1 semicircle. Okay, we are looking for the absolute maximum value of f, not f prime, but f over the closed interval from -6 to 6. Okay, so let's think back to the last chapter. For finding absolute extrema, we need to first consider our critical points. Critical points can happen where the derivative, so f prime, equals 0 or doesn't exist, Or we also have to consider as candidates endpoints of the closed interval, which we do have a closed interval from -6 to 6. Okay, so for our critical points, let's start by asking, where does this function f prime equal 0 or not exist? Well, it exists everywhere on -6 to 6. Don't get confused. I don't want to know where the derivative of this doesn't exist. I want to know where this function doesn't exist, but it's defined everywhere on the closed interval. It does equal 0, though, at -4, -2, 2, and 5. So -4, -2, 2, and 5. Okay. And then we also need to consider our endpoints of -6 and +6. Okay, so we actually have a lot of candidates to test for. So I'm going to try and start over here to the left. So let's just go left to right. So f of -6 is going to be equal to, actually, I don't want to write it in that order. Okay. Because we haven't talked about properties where we go backwards in integrals. I'm going to start over on the right side, actually, and then we'll come back. So f of 6 is going to be equal to f of 0, which is 3. This is given to us. So f of 0 plus the accumulation from 0 to 6 of f prime of x dx. Okay, so f of 0 is 3, and then the integral from 0 to 6 would be this part but negative, this part but positive, and then this part negative again. So geometrically, I'm looking at this, and this little triangle and this little triangle undo each other because this is subtracted. This part right here is subtracted from that. So I really just need to figure out what this is and what this is. So the area below here, again, we have a quarter circle with the whole circle would be area of 4 pi. So that's just pi. Let me unscribble on this. So this is pi. And then this whole, let me get rid of all these scribbles. Okay, this whole triangle is a 1, 2, 3 by 2. So it has an area of 3. But then this right here has an area of 1/2. So we're going to do 3 plus, and then here we've got a negative pi plus 3 minus 1/2, which is 6 minus 1/2 would be 11/2 minus pi. Okay, that's f of 6. And when we start comparing, we can say that's a little bit bigger than 3, and then we can see where that decimal lands. So without having to rewrite full integral statements, let's see if we can kind of figure out these other ones. Well, f of 5 is going to be f of 0, the same thing, 3, and then we're only doing the integral from 0 to 5. In other words, we're not subtracting that 1/2 right there. So it's going to be 1/2 bigger than this, so it's going to be 6 minus pi. Okay, you can write out a full statement like this if you'd like, but I'd rather just kind of undo some of this geometrically. Okay, so that's f of 5. F of 2, again, I'm moving right to left here. F of 2 is equal to, so now it's the original amount, 3, and I'm just adding this area right here, which is actually being subtracted, so that's going to be 3 minus pi. Okay, but now it gets a little bit trickier because the other points, -2, -4, -6, are to the left of 0. We do have some properties that can allow us to go from right to left, but we haven't talked about those yet. So I'm going to use the full FTC expression and then rearrange it kind of like I did with example or part A of example 2. So I'm going to give myself just a little more room to do this. Okay, so from -2 to 0, I know I'm essentially going from 0 to -2, but from -2 to 0, I can say the integral from -2 to 0 of f prime of x dx is equal to capital F of 0 minus capital F of 2. Okay, then the integral from -2 to 0 of f prime is another pi, but below the x-axis, so negative pi, So negative pi equals f of 0, which is 3, minus f of 2. Moving f of 2 over, moving the pi over, I get f of 2. Oh, I'm sorry, negative. This should be negative 2. Negative 2 equals 3 plus pi. Okay, so there's that value. So I've got this one, I've got this one, this one, I've got this one. Okay, and so then I need to do negative 4 and negative 6. I'm going to come over here. Sorry, I'm a little all over the place. F of, the integral from negative 4 to 0 of f prime of x dx is equal to f of 0 minus f of negative 4. Again, this is a 3. The integral from negative 4 to 0 is, well, I've got an area of 1 on this little triangle, but then minus pi. So I have 1 minus pi. So I get f of negative 4. Cheating a little bit here. F of negative 4 equals 3 minus 1. So 2 plus pi, okay? And then lastly, f of negative 6. So the integral from negative 6 to 0, oops, that's a 0, of f prime of x dx equals f of 0 minus f of negative 6. And now I've got an area of negative 2, or not an area of negative 2, an area of 2, but it is being subtracted. So negative 2 plus 1 minus pi is negative 1 minus pi. F of 0 is 3. Okay, so f of negative 6 is 4 plus pi. All right, so then for the absolute max value, we are comparing all of our candidate values. Well, 3 minus, let me switch colors. So I've got a 6 minus pi right here, which is going to be slightly bigger than 5.5 minus pi. And it's also bigger than 3 minus pi. It's, let's see, 3 plus pi. Oh, okay. So now we've got 3 plus pi is bigger than 2 plus pi. 4 plus pi is bigger than 3 plus pi. So now I'm comparing 6 minus pi and 4 plus pi. 6 minus pi is 6 minus 3 point something, which is going to be 2 point something. And then here, 4 plus pi is going to be 7 point something. So this is my maximum value. So maximum value is 4 plus pi.